Hi and welcome to another organic chemistry lesson. In this one we are looking at haloalkanes, their properties and their reactions. Let's start with their properties. Well, you'll recall that when we work with hydrocarbons or with the organic molecules, we had carbon bonds, and these carbons and the hydrogens had more or less the same electronegativity. And what that means is that at any time they are drawing the electrons in themselves with the same passion, you can almost say. So in other words, this carbon is attracting electrons more or less the same as that hydrogen is attracting them. So the electrons are more or less evenly distributed. But at any one time, the electrons can all of a sudden group themselves at different places, and the longer this chain is, the more likely it is that those electrons can be grouped together. Now this causes a temporary unequal distribution of the electrons, and because of that, at some point, for some reason or another, the one part of this electron is slightly more, the one part of this molecule is slightly more negative than another part of the molecule, causing a dipole moment. Okay, and this is called induced dipole. Okay, dipole. Dipole meaning there's two poles, a positive and a negative. Induced meaning that it is not permanent. It is a temporarily induced dipole. Okay, now what happens is the moment we have a more electron negative atom in a molecule than the rest of the atoms, then even though it's maybe not a permanent and a strong difference like in ionic bonds, these clear dipole connections. But if we were to look at an example of, okay, let me show you the example of in a, okay, if we have our carbons here and bonded to our carbons we have our hydrogens. So these are my hydrogens, but then here I've got a chlorine. Okay, so I've got my chlorines coming up. There I've got my chlorine bonded to this. So what will this one be called? Well, we have a chlorine bonded on the second carbon, so this would be 2-chloro, and we've got 3 carbons, so that's propane, 2-chloropropane. Now in this case we all of a sudden have a chlorine. Now what you have to remember is that and this is obviously called a haloalkane because we have a halogen. You have to remember that halogens are in the 7th column. Now in the 7th column we only need one more electron to fill up our highest energy level. So as you can see, these elements here have a very high desire for an extra electron, making their electron negativity the highest of all the others in on the table. So you can see this one is, for example, 3.98, chlorine 3.14. The only other one that has a higher electron negativity is oxygen. Bromine is the next one, and so the group 7 elements have a much higher electronegativity than the rest. So when it comes to carbon, which has an electronegativity of 2.55, and hydrogen at 2.2, chlorine is at 3.16. Okay, bromine is slightly more, slightly less, more than carbon and hydrogen at 2.96, and iodine also just slightly more. And so, but when it comes to haloalkanes, we have that our it's not anymore induced dipole. Now we've got one atom that has a slightly higher electronegativity. So what would happen is there's a very good chance of electrons grouping together nearer that that element in this compound. So there's a very high likelihood of having more electrons near here. And now it is called a dipole. It's a dipole forces. That's the type of forces that work here. So dipole forces are stronger forces than induced dipole. It's still not very strong, but it's still stronger than induced dipole. And so what we would find is that if I had a 3-carbon, if like in this case I've got a propane at a certain, so propane's boiling point is at negative 42 degrees Celsius, while 2-chloropropane's boiling point is at 36, roughly 36 degrees Celsius. Okay, so it's really clear that the moment that we add a halogen, we really increase the strength of the forces that are active in the molecule. So that's the one element of the properties. The rest still applies. The longer the chain, the stronger the forces. The more branches there are, the stronger the forces. The weaker the forces, because now they can't fit nicely together as they would have if there were few branches. So all of that still applies, that applied to the hydrocarbons that we looked at earlier. But in this case, even the position of the chlorine would make a difference. So for example, a chlorine here, okay, on the second carbon, it kind of causes a problem, because if it was on the side here, then it would also make this molecule much easier to connect to other molecules. So the fact that it is here on the side also makes a difference, and if there's 2 chlorines, it obviously also makes a difference, especially when it comes to symmetry. But that is not so important for this course. For now, all that is really important is the fact that haloalkanes have dipole forces, which increases the strength of the forces, making certain properties to be affected. For example, it would have a higher boiling point, okay, because the molecules attract each other with greater forces. Okay, it will have a lower vapor pressure. Remember, vapor pressure refers to molecules that can escape from the liquid, causing a vapor, and if that vapor was to be contained, it would cause pressure. And since the fewer of the molecules will escape because they are attracting one another, the vapor pressure will be less. So the vapor pressure will be reduced, and then also viscosity, okay, the measure of the resistance to flow. Viscosity in this one will be higher, so it will, as a liquid, it would be more resistant to flow, because the molecules want to stay together, so they don't want to flow around very easily. Okay, so with that in mind, I hope you understand that haloalkanes have stronger forces, intermolecular forces, than the normal hydrocarbons. In the next video, we'll look at some reactions. I'll see you there.